During the 12 years of National Socialist rule, and particularly throughout the Second World War, Germany emerged as a military powerhouse whose machinery appeared unstoppable. With unprecedented speed and might, the Third Reich carved a path of conquest and territorial expansion across Europe. Adolf Hitler spurred aeronautical innovations that transformed the technology of the era. In just one decade, Germany produced breakthroughs such as radar, stealth aircraft, jet-powered planes, and even preliminary spacecraft concepts, leaping decades ahead of other nations. The formidable Waffen-SS distinguished itself through its use of advanced weaponry, including the MG-42 machine gun, celebrated for its high rate of fire and reliability, as well as submachine guns like the MP-40, compact and highly effective in close-quarters combat. One of the most revolutionary pieces of German technology was the Messerschmitt Me-262, the aircraft that altered the rules of aerial warfare. The Me-262 was the world's first operational jet fighter, with development beginning in 1938 under the supervision of Wilhelm Mattel, after the Reich Aviation Ministry commissioned the creation of a jet-powered plane. Although jet aircraft had been tested before the outbreak of World War II, it was not until the later stages of the conflict that this particular fighter entered service, heralding a new era in military aviation. The design underwent multiple revisions before its final form. Originally, the engines were to be mounted at the center of the wings, with the landing gear beneath the cockpit. This arrangement was later altered, and the wings were swept back, giving the plane its distinctive arrow-like silhouette. By mid-1940, plans were approved, and production of the first prototypes began. 3 test aircraft were constructed, though the jet engines were still under development. The first prototype flew on April 18, 1941, powered by a conventional Jumo 210G engine. The flight succeeded, but it was not until November 1942 that the first trials with the final turbojets, capable of 450 kilograms of thrust, were conducted. The Me-262 was designed for multiple combat roles: fighter, interceptor, attack bomber, reconnaissance aircraft, and night fighter. Its speed was among its most remarkable features, exceeding 500 km per hour, making it significantly faster than many Allied fighters, such as the North American P-51 Mustang. Despite its velocity, the aircraft remained vulnerable during takeoff and landing due to limited maneuverability in these phases. Consequently, the airfields from which it operated were defended by other fighters, such as the Focke-Wulf FW-190D9. Mass production began in July 1944, with roughly 1,400 to 1,500 units built, though only about 300 saw operational service. Despite its limited use, the Me-262 managed to shoot down over 500 Allied aircraft. Its technological superiority was evident, yet logistical obstacles and production challenges, including Allied bombing raids and resource shortages, prevented it from decisively altering the outcome of the war in favor of the Axis. The Me-262 left a lasting legacy. Its revolutionary design transformed military aviation and laid the groundwork for subsequent jet aircraft, influencing later models such as the North American F-86 Sabre and Boeing B-47. Beyond this landmark aircraft, Nazi Germany developed around 100 innovative and notable aircraft designs during the Second World War. The Horten Ho 229, for example, was a remarkable flying wing incorporating dual propulsion systems, providing an aerodynamic structure for rapid, powerful strikes. Its plywood construction made it lightweight yet stable, with impressive payload capacity. Another striking example was the Bakhemba 349, capable of vertical takeoff. After completing its attack, the pilot could eject via a parachute system, though only a few prototypes were built during the final days of the regime. Shock troops, the innovation and legacy of tanks in modern warfare. The evolution of tanks began in the First World War, a conflict that saw the creation of the first armored vehicles as a response to difficult terrain filled with barbed wire and machine gun fortifications. Britain pioneered the development of these vehicles, with officers Ernest Swinton and Maurice Hankey playing key roles in conceptualizing the initial prototypes. The first British combat tank, Little Willie, proved unsuitable for the battlefield but laid the foundation for Big Willie, which became the prototype for the Mark I, the first operational combat tank. During the 1920s and 1930s, tanks continued to advance, particularly in France and Germany. The French Renault FT-17 revolutionized tank design with a fully rotating turret-mounted gun, a feature that remains standard in modern tanks. With the outbreak of World War II, tank development reached new heights, especially in Nazi Germany, which experimented with increasingly advanced models to meet the demands of the conflict. Under General Heinz Guderian, Germany refined the use of tanks as an independent force capable of rapid advances in penetrating enemy lines, revolutionizing mobile warfare and influencing other nations to recognize the strategic importance of armored units. German tank models evolved significantly during the war. The Panzer III and Panzer IV were the most common early war tanks, though they struggled against the Soviet T-34, renowned for its sloped armor, mobility, and firepower. To counter this threat, Germany developed the Panzerkampfwagen V, known as the Panther, in 1943. This medium tank excelled in balancing mobility, armor, and firepower, making it one of the most formidable tanks of the era. Its maneuverability combined with its 7.5 cm gun rendered it a fearsome adversary on the battlefield. Presence on the battlefield and is widely regarded as one of the best tanks of the conflict. However, German advancements did not stop there. Concurrently, the Panic-Kampfwagen 6, known as the Tiger, was being developed. This heavy tank, which entered service in 1942, became renowned for its powerful armor and 8.8 cm gun capable of destroying almost any other armored vehicle of its time. Despite its strengths, its weight and manufacturing complexity rendered it less practical than lighter models. By the end of 1944, Nazi Germany had introduced an improved version of the Tiger, the Krieg Tiger or Tiger II, which further increased its armor and firepower. However, it suffered from the same logistical and mobility issues as its predecessor's impact and limitations. Although this heavy tank was formidable in combat, it failed to significantly alter the course of the war due to production and deployment limitations. Beneath the waves, the legend of U-47 and its Wolfpack tactics. One of the most iconic German submarines was U-47 Type 7B vessel. It was commissioned on the 17th of December, 1938, and its operational life was relatively short. During its 10 missions, it sank 30 ships totaling 164.50 to gross registered tons and damaged 8 more, adding 6,275 gross registered tons. This submarine represented a significant advancement in submarine technology of the era, measuring approximately 67 m in length and 6 m in width. It offered excellent maneuverability and the ability to perform rapid underwater maneuvers. It was designed to carry a crew of between 44 and 48 men and was equipped with 6 torpedo tubes. Submarines of this class could dive to depths of up to 230 m and operate up to 250 nautical miles underwater before needing to surface to recharge their batteries. These submarines were renowned for their speed and ability to quickly evade detection, strategic impact, and the Scaflow operation. The strategic impact of U-47 was particularly evident during one of its earliest and most notable missions, the attack on the British naval base at Skara Flow in October of 1939. This daring operation was led by Lieutenant Preen aboard the submarine. On the night of the 13th to the 14th of that month, Preen successfully infiltrated the heavily fortified British naval base, considered nearly impenetrable, by taking advantage of the darkness and favorable currents. After careful maneuvering, the submarine positioned itself to attack the battleship HMS Royal Oak, which was anchored in the bay at 1:30 in the early morning. Preen launched torpedoes that struck the Royal Oak, causing a devastating explosion that sank the ship and resulted in the loss of 833 of its 1,400 crew members. This success bolstered confidence in the capability of German submarines to operate in heavily defended British waters, solidifying the submarine warfare strategy championed by Admiral Karl Donitz. Wolfpack tactics. The Rudel tactic or Wolfpack tactic was central to the operations of U-47. In this approach, multiple submarines coordinated attacks on enemy convoys, significantly increasing the chances of success while complicating the Allied defense efforts. This tactics effectiveness was demonstrated across numerous missions where U-47 and other German submarines inflicted severe damage on Allied supply lines, significantly contributing to Britain's supply challenges. U-47 became a symbol of the German Navy, especially after its victory at Scapa Flow. Following this success, the submarine adopted the emblem of a snorting bull, which later became the insignia of the 7th U-boat flotilla. The mysterious disappearance of U-47, however, not all S ended successfully. U-47 disappeared under mysterious circumstances in March of 1941. The exact cause of its sinking remains unclear, with theories suggesting it may have fallen victim to an Allied attack or suffered a technical failure that caused its demise. Other notable vessels: the Tirpitz and U-505. Another remarkable vessel was the Tirpitz, the largest battleship of the CS Marine and the sister ship to the Bismarck. The Tirpitz entered service in 1941 and posed a constant threat to Allied convoys in the North Atlantic. Its impressive 38 cm guns allowed it to strike targets at long distances, making it a formidable adversary. However, despite its strength, the turrets never secured a decisive victory and was ultimately sunk by Allied airstrikes 3 years after it began operations. Germany also deployed U-505, a Type 9 class submarine known for its long range, capable of traveling over 27,000 kilometers. It gained fame for its effectiveness in sinking Allied merchant ships during the Battle of the Atlantic. On the 4th of June, 1944, U-55 was captured by the United States Navy during a daring and covert operation. At the time, it was on its final patrol in the Atlantic after having sunk several Allied ships throughout its career. During one mission, it was detected by Task Group 22.3, which had been tracking its movements. The submarine suffered severe damage from depth charges launched by us ships, forcing the crew to prepare to abandon it. Before doing so, they opened the valves to scuttle the submarine and prevent it from falling into enemy hands. However, in a desperate twist, U.S. forces managed to board and secure the submarine before it completely sank. Significance of the capture of U-505. The capture of U-55 was significant as it marked the first enemy submarine captured since the War of 1812. On board, valuable documents and an Enigma machine were discovered, providing crucial intelligence that aided the Allied war effort. Wernher von Braun and the V2. The duality of science in times of war. The story of the V2, one of the earliest and most advanced missile weapons perfected during the Second World War, dates back to the late 1930s. Research and development of this technology took place at the Heisverukel Punda, located on the island of Ustum in the Baltic Sea. Wernher von Braun, a prominent engineer and rocket scientist, led the project, which was initially known as the A4. This initiative pioneered the use of liquid fuel, granting greater efficiency and range compared to solid fuel rockets. The first successful flight of the A4 occurred on the 3rd of October, 1942, reaching an altitude of 84 kilometers, placing it at the edge of space. This achievement marked a milestone in rocket technology and laid the groundwork for the subsequent development of the V2 production and wartime deployment. Following an air raid on Punda in August of 1943, production of the devices was moved to less vulnerable areas. This relocation led to the establishment of the M-Bora concentration camp, where forced labor was used to manufacture the rockets. A year later, the A4 war was renamed Vergeltungswaffe 2 or V2 as part of the Nazi regime's propaganda effort to present the weapon as a decisive factor in the conflict. It was promoted as a response to Allied bombings, with expectations that it would turn the tide of the war in Germany's favor. Wernher von Braun, though deeply involved in the military goals of the Third Reich, also dreamed of future space missions, adding an intriguing dimension to the development of this device. Technical features of the V2. From a technical standpoint, the V2 was among the first large-scale liquid-fueled rockets, measuring 14 m in length, with a diameter of 1 m 65 cm. It weighed between 12,700 and 12,900 kilograms when fully loaded. Its payload capacity was 750 kilograms and it had an approximate range of 300 km. The V2 could reach an altitude of up to 80 kilometers and had a flight time of roughly 320 seconds. The propulsion system of the V2 consisted of a liquid-fueled rocket engine powered by a mixture of alcohol and liquid oxygen. This engine generated approximately 270 tons of thrust, equivalent to about 650,000 horsepower. The V2 could achieve speeds of up to 5,500 km per hour, making it nearly impossible to intercept during its trajectory. Designed as the world's first ballistic missile, its trajectory could not be altered once launched. The rocket followed a parabolic path, enabling it to strike targets at long distances with high precision. Operational use. The first V2 operations began in September of 1944, targeting London. These attacks were part of a strategic offensive aimed at demoralizing the British population and easing pressure on German forces. The V2 represented a significant shift in warfare as it was practically undetectable by contemporary defense systems. Its destructive power was devastating, resulting in thousands of civilian deaths and significant infrastructure damage. However, despite its impact, it failed to decisively alter the course of the war. By late March of the final year of the Third Reich, just before hostilities in Europe ended, more than 3,000 V2 rockets had been launched, with London and the port of Antwerp as primary targets. It is estimated that between 8,000 and 12,000 people died in London due to these attacks, and the destruction of infrastructure was extensive, with thousands of buildings damaged or destroyed. A lasting legacy. The V2 is likely one of the most iconic examples of the technological advancements of its time, leaving a lasting legacy in the history of rocketry, ciphers, and conflict. The Enigma as the Third Reich's secret weapon. The story of the Enigma machine began in 1918 when German engineer Arthur Scheres patented its design. Initially conceived for commercial applications, Scheres recognized the potential of encryption technology for securing communications. 5 years later, he founded the Schiffemaschine in Action Gazelle shaft, commonly known as CHIM, to market his invention. The first model produced encoded text on paper resembling a typewriter in 1924. An improved version was introduced that displayed letters through lights, making it more user-friendly and accessible for operators. How the Enigma worked. The Enigma was based on a rotor design that encrypted messages through a complex combination of electrical connections. Each rotor had 26 contacts on both sides, connected by internal wiring. When a letter was pressed on the keyboard, the electric current flowed through the rotors, being redirected by the internal wiring of each rotor before passing to the next. This setup ensured that each letter was replaced with another, creating a simple yet effective cipher. By 1926, the German Navy was the first to adopt the machine, followed by the Luftwaffe and the Army. The Enigma became an indispensable tool for secure military communication. Key improvements. Technological enhancements were quickly implemented to adapt the machine to the military's specific needs. One of the most significant changes was the addition of a plugboard, which allowed additional permutations, thereby increasing security. These modifications led to the development of the Enigma 1, which was officially adopted by the Reich on the 1st of June, 1930. Its military introduction represented not just a technical leap, but a strategic advantage for the German armed forces in the lead-up to the Second World War. Enigma's widespread use. It is estimated that between 100,000 and 200,000 units were produced, making the Enigma a widely used tool for military communication throughout the war. The machine enabled the German forces to transmit orders and secret information incomprehensible to the enemy. This was particularly critical in strategic operations, where securing information about troop movements and attack plans was vital. A particularly significant use of the Enigma was in submarine operations, the German submarine fleet, often operating in coordinated groups called wolf packs, required a secure communication method to coordinate their maneuvers. The Enigma allowed submarine commanders to transmit orders and information about enemy ship movements quickly and securely. Overconfidence and security. German high command believed that the machine's encryption ensured unbreakable communication security. This overconfidence led them to continue relying on the Enigma, unaware that Allied forces had already begun decoding their messages. This critical oversight proved to be a significant error, as cracking the Enigma codes during the Second World War became a turning point in the Allied effort to disrupt German communications. Breaking the Enigma codes before the outbreak of hostilities. Polish mathematicians had made significant breakthroughs in deciphering the Enigma. They shared their findings with the British after the German invasion of Poland. Mathematician Alan Turing joined the government code and cipher school at Bletchley Park. Focusing on improving Polish methods, Turing and his team developed the bomb, a machine designed to automate the decoding process. This innovative device could quickly test possible rotor combinations, simplifying the identification of the codes used in German communications. Bletchley Park role as the war progressed. Efforts at Bletchley Park intensified. By 1943, the bomb machines were decoding up to 84,000 messages per month, providing critical intelligence about German movements. Turing not only contributed to the decryption of Enigma but also laid the foundations of modern computing. demonstrating how the combination of mathematics and technology could change the course of history. Between light and darkness, German innovations in radar and night vision. The Freya radar, developed before the Second World War, was one of the first systems of its kind employed by the Third Reich, named after the Norse goddess Freya. Its designation reflected its strategic importance. The radar was designed to provide complete 360 degrees coverage and operated at frequencies between 120 and 130 ms, with a pulse power output ranging from 10 to 15 kW per hour. Although its range could extend up to 160 km, the Freya radar's primary advantage lay in its complete mobility, offering critical flexibility to adapt to changing battlefield conditions. Key role in air defense. The Freya radar became a cornerstone of German air defense and early warnings of air raids. This allowed for better coordination and response to enemy attacks, particularly in intercepting Allied aircraft through its integration into the Kammam-Hubbalina complex system of radar stations, night fighters, and anti-aircraft batteries. The radar played a crucial role in improving coordination among various defense units. However, it faced significant challenges in determining the precise altitude of enemy aircraft, making it less effective than the British chain home system in PP point accuracy. Additionally, the radar's effectiveness was reduced during the war's later stages due to countermeasures like duple small aluminum strips deployed by the Allies to jam German radar systems. Improvements and successes. Despite its limitations, the Freya radar proved vital in enhancing German response capabilities. Upgraded versions such as the FG4001 and FG41 were developed to improve both range and accuracy. ACCY by incorporating multiple antenna arrays, addressing some of the original model's shortcomings. ZAL Garrett 1229, the Vampire night vision device. Another significant advancement in German military technology was the ZAL Garrett 1229, known as the Vampire. This active night vision system was designed to integrate with the Sturg 44, the famous German assault rifle. The ZAL Garrett 1229 used active illumination technology to generate image in the dark, enabling German soldiers to fight effectively in low visibility conditions. This innovation provided a significant tactical advantage, allowing for surprise attacks and improved defensive capabilities during nighttime operations. Challenges and limitations. However, the Vampire's availability was extremely limited due to the complexity of its manufacturing process and the dwindling resources of the Third Reich. During the war's final years, only a small number of soldiers had access to this equipment, which reduced its overall impact on the conflict. Additionally, the active illumination technology required a specific type of infrared light which was not suitable for all environmental conditions. Furthermore, operational challenges in various terrains and weather conditions hindered its effectiveness in certain combat scenarios. While this system represented a significant improvement in night combat capabilities, its large-scale deployment was not feasible, limiting its real-world impact. The bigger picture. As the war progressed, Nazi Germany sought to enhance these technologies further. However, resource shortages and the pressures of total war prevented many of these innovations from making a decisive impact. Precision weapons. The innovation and limitations of the Fritz X. The Fritz X was one of the most innovative weapons developed by the Third Reich, marking a milestone in the evolution of precision-guided munitions during the Second World War. Its creation arose in the context of escalating aerial warfare, where Axis powers sought to counter the Allies' growing superiority in this domain. Engineered by German designer Max Kramer under the direction of the RU Style Company, the Fritz X was intended to provide an effective solution for destroying powerful and heavily armored enemy ships, which posed a significant challenge to conventional weapons of the time. The first mass-produced guided bomb. The Fritz X was the world's first mass-produced guided bomb. This missile-like weapon, launched from an aircraft, was specifically designed to attack armored ships weighing 1,570 kilograms and measuring 3.5 meters in length. With a wingspan of just over 1.2 m, the Fritz X was capable of penetrating up to 20 centimeters of steel plating, making it a lethal threat to warships equipped with a powerful radio-based remote control contract system. The bomb utilized amplitude-modulated frequencies of 50 MHz, allowing it to be guided from the attacking aircraft to its target. However, the bomber needed to fly low and circle above the target to manually guide the device, which limited its effectiveness and required a high degree of skill from the crew. Introduction and first successes. The Fritz X was officially introduced in July of 1943 and saw its first combat use on August 29 of the year. One of its earliest and most notable successes occurred on September 9 during a tragic episode involving the Italian battleship Roma, the pride of the Regia Marina, following Italy's armistice agreement with the Allies. The Roma and other vessels departed the port of La Spia intending to surrender. While on route to the port of Bona, the ships were spotted by the German Luftwaffe near the Strait of Bonasia at 4:35 in the afternoon. A group of Dornier Do 217 bombers released 2 Fritz X bombs onto the battleship. The first bomb struck the side of the Roer, causing severe damage by flooding vital compartments and slowing the ship's speed. The second bomb proved catastrophic, hitting the magazine and triggering a massive explosion that destroyed much of the vessel, killing hundreds of sailors, including Admiral Carlo Bergamini. The Roma broke apart and sank quickly, claiming the lives of over 1,000 crew members. Limitations and challenges. Despite its innovative design, the Fritz X faced significant logistical and tactical challenges: aircraft scarcity, a shortage of bombers capable of carrying and deploying the bomb restricted its battlefield use; precision issues, its accuracy was relatively limited, reducing its effectiveness in some combat situations; operational risks, the attacking aircraft had to fly at low altitudes, exposing it to substantial risk, particularly as Allied anti-aircraft defenses improved. Alternative innovations, the Heinel H's 293. In addition to the Fritz X, the Germans developed the Heinzel H's 293, another weapon designed to target ships. Unlike the Fritz X, this bomb featured a different control system. Instead of requiring the aircraft to remain over the target, it could be guided via cables. From Allied victory to the Cold War, the sea of Nazi technology and its aftermath. After the conclusion of the Second World War, the world underwent a period of radical transformation. The victorious Allied powers, having defeated the Nazi regime, faced a new challenge: the need to access and exploit the vast scientific and technological knowledge that Germany had developed over many years. This effort was not only crucial for rebuilding their own industrial and military capabilities, but also became a central element of the emerging Cold War between the Western powers and the Soviet Le Bloc. Operation Paperclip harnessing German expertise. One of the most significant programs in this context was Operation Paperclip, carried out over 4 years starting in 1945. The secret United States program brought more than 1,600 German scientists, engineers, and technicians to American soil. Among them were prominent figures like Wernher von Braun, renowned for his work in perfecting the V-2 rocket. Operation Paperclip was directed by the Joint Intelligence Objectives Agency, whose primary goal was to ensure that these experts did not fall into the hands of other Allied powers, particularly the Soviet Union. However, the United States was not alone in seeking to capitalize on German technology. Nations like Britain, France, and the Soviet Union also actively recruited German scientists beyond Paperclip. Operation Elos and nuclear ambitions. This phenomenon of talent acquisition extended beyond Paperclip with initiatives such as Operation Ulsos, part of the Manhattan Project. Its main objective was to investigate and secure advancements in Germany's nuclear program, fearing the potential development of an atomic bomb. Beginning in 1944, the operation was led by physicist Samuel Gmi and Colonel Boris Pash. As Allied troops advanced across Europe, a small team of scientists and military personnel infiltrated liberated areas to gather information on German nuclear research. Despite some initial setbacks such as the capture of relatively unknown scientists, the mission yielded critical results in Hingen, where documents revealed that Germany was far from developing a functional atomic bomb. By April of the following year, Ulsos agents captured prominent German physicists including Otto Hahn and Werner Heisenberg, preventing their knowledge from falling into Soviet hands. The detained scientists were transferred to Farm Hall in England, where they were monitored to extract information about their research. Operation Backfire, testing the V-2 rocket. Another notable effort was Operation Backfire, a combined military and scientific mission carried out by the Allies, primarily British personnel, at the conclusion of the Second World War. Its goal was to assess the V-2 rocket developed by Germany and to study its technology. The operation took place in 1945, during which several V-2 rockets were launched from the Netherlands into the North Sea. British engineers conducted successful tests, achieving greater precision compared to the German wartime launches. These trials revealed significant innovations in rocket engineering, including advanced propulsion systems and sophisticated guidance mechanisms. The Cold War race for technology. The acquisition and exploitation of Nazi technology had a profound influence on the rivalry between the United States and the Soviet Union. Both superpowers quickly recognized the strategic importance of German wartime advancements. While the United States gained from captured German equipment and technical expertise, the Soviet Union similarly utilized these resources to accelerate its own technological progress. The competition spanned multiple fields, especially space exploration, as both nations sought to assert their scientific dominance. The Soviet Union's launch of Sputnik 1 in 1957 marked a pivotal moment, sending shockwaves through the Western world. This achievement, known as the Sputnik shock, sparked fears in the United States of falling behind in the technological race and led to substantial investment in research, development, and both the arms and space races. The contest over German-derived technology intensified superpower tensions, with each new innovation by the opposing side, no matter how modest, perceived as a national security threat. This dynamic accelerated the arms race, encompassing not only military advancements but also civilian achievements, including space exploration. In response, the United States poured resources into programs such as NASA, aiming to maintain its leadership in the extraterrestrial domain.